Hello students, welcome back. In this part, we will discuss about metallic solids and covalent solids. So here I have one question for you. You all know that diamond is the most hardest substance ever known. So what makes the diamond the most hardest in the entire universe? You will get the answer to this question if you go through this particular part. Okay, let's start. So now we are going to learn about the other two types of solids. So we already discussed about the two types of crystalline solids, and the remaining two types are metallic solids and covalent solids. So first we will start with our discussion with the metallic solids in this part. Okay. So what are metallic solids? What are metallic solids? So most of the information that you can understand from the name itself, metallic solids, that means these are metals. Okay, because metals are solids, so that's why metallic solids are nothing but metals. So we know that metals are orderly collection of positive ions which are surrounded by and held together by sea of free electrons. Okay, so I'll make you understand from this picture. So if you take a piece of any metal, say if I take a piece of copper, what it contains? It contains copper atoms, right? So it contains copper atoms. So we know that metals have a tendency to lose their electrons easily. So in this piece of copper, let us assume that this is a piece of copper I have taken. So these are copper ions, Cu+, and each copper atom has given out one electron. So this one is an electron which is given out by this copper atom, and as a result this is a copper ion Cu+, and this is electron given out by this copper atom. Okay. So here if you see, it is containing copper ions as well as electrons. Electrons are shown in this yellow color. These are all electrons, and these are all positively charged cations, okay, which are copper ions. So if you see, these metal ions are static, they don't move freely inside the metal. Only these electrons are capable of moving inside the metal, and whatever the space available, the space for their movement, they'll randomly move from here to there and they'll form a sea of electrons. So here it all looks like a sea of free electrons. These are free electrons which will move freely inside the metal, and so it is an orderly collection of positive ions which is surrounded together. These positive ions are surrounded by, and these positive ions are also held together by these electrons. Okay, so we'll discuss more about it. So we know that these electrons are mobile, they are free electrons, and they are evenly spread out throughout the crystal. So okay, if you see here, see, each electron is given out by, this electron is given out by this atom, this electron is given out by this atom. Okay, so here, but these ions are static, but electrons are not static. They move in the space available for them, in the vacant space, and it looks like this. Here you can see it looks like a sea of delocalized electrons. So here concentrate on this term, delocalized. Localized means they are situated at one place, but delocalized means they are not situated at one particular place, but they roam everywhere inside the metal. So these electrons are mobile electrons or free electrons, and they are spread out evenly throughout the crystal. Okay. Yeah, as I said before that each metal atom contributes one or more electrons towards the sea of mobile electrons. So if I take example alkali metals like sodium, potassium, they have only one valence electron and they only contributes one electron, right? Sodium and potassium, they only contributes one electron. But if you take magnesium, calcium, which are having two valence electrons, so these are capable of contributing 2 electrons. Okay. So later if you go to next group, aluminium, they are capable of donating 3 electrons, right? They are capable of losing 3 electrons. So here what you need to understand is that these mobile electrons are given out by each metal atom, okay, which contributes 1 or 2 or 3, etc. Because of these free and mobile electrons, the metallic solids are high electrical as well as thermal conductors, because they act as carriers of electricity. So that's why they are good electrical conductors, and they also act as carriers for conduction of heat. So that's why they are also good thermal conductors. So metals are good electrical conductors and they are also good thermal conductors. So please remember this thing. They are good electrical and thermal conductors because of the presence of free and mobile electrons. Okay. And metals are highly malleable and ductiles. So metals are highly malleable. So what is malleable and what is ductile? So malleable is nothing but the metals. What you can do is you can deform a metal and you can transform it into a sheet of metal. You can make a sheet. If you take aluminium, if you take copper, we can mold these metals into a sheets. Okay. So only metals has this kind of flexibility. All others cannot have. So that's why the metals are malleable. And ductile is the ability of a material to form thin wires. Thin wires. If you take copper wires, right? The very thin wires you can make from copper, because copper is a ductile. Okay. And similarly, some other metals you can take, they have a capability of deforming or transforming into a thin wire. Okay. So ductile is the ability of a material to form wires, and malleability is the ability of a material to form thin sheets. Okay. So metals are highly malleable and they are ductile. So this is all about the metallic solids. So next we will discuss about the covalent or network solids. Okay. So covalent or network solids. So what I mean by covalent and network solids? So as usual, concentrate on this term, covalent solids. So covalent solids are nothing but these are solids which are made up of atoms, like which are held together by covalent bonds. Simple, right? So definition you can easily understand. So which are formed by the covalent bonds between the adjacent atoms throughout the crystal. So the adjacent atoms, they form covalent bonds, and this type of bonding extends over. So this type of bonding you will observe throughout the crystal. So that's why it is also known as network solids, because here we have a network of bonds, network of covalent bonds. So the covalent solids are also known as network solids. And we know that covalent bonds are formed by the sharing of electrons, and these covalent bonds are strong as well as they are directional in nature, right? They are directional in nature. Therefore, atoms are held very strongly at their positions. They are held very strongly at their positions, and because of this thing, because of the strength of the covalent bond is high, these solids are very hard and brittle. They are having high hardness and they are also brittle. They don't get deformed. They are brittle in nature. And they also have extremely high melting points. Extremely high melting points. So some of the examples of covalent solids include diamond, graphite and silicon carbide. So diamond and graphite are the famous examples of which are allotropes of carbon, which are crystalline solids under the category of covalent or network solids. Silicon carbide is also one of the example of covalent or network solids. So here we will discuss more about this diamond and graphite and their properties. So diamond is a covalent solid and it is very, very special, right? Because of its extreme hotness and high thermal conductivity. So if you see such notable, or I can say the different physical properties the diamond can able to exhibit only because of this network, the covalent network it has. So the diamond is a transparent crystal of tetrahedrally bonded carbon atoms in a covalent network lattice, where you can see in this picture. in this image where each carbon is forming 4 bonds and it is having, each carbon is having an hybridization sp3 hybridization, so which is a tetrahedral. So it is a crystal of tetrahedrally bonded carbon atoms in a covalent lattice that crystallizes into the diamond lattice. Okay, so this 154 pm picometers is the CC bond distance. Yeah, you can also see in this image, you can also, the black ones are the carbon atoms, so which are tetrahedrally bonded carbon atoms, and this is it is a lattice, is a covalent network lattice. Okay, so yeah, as I said before, its most notable properties are its extreme hotness, where you can cut or you can scratch a diamond only with a diamond, right? Even if you want to scratch a diamond, that is only possible with a diamond. So this is because of its extreme hardness and thermal conductivity. It also has high thermal conductivity, but remember, it is not a electrical conductor. Because of absence of free electrons, it does not conduct current. And next is, the next important covalent solid is graphite. So graphite is also important thing. So carbon atoms are arranged in different layers. So whatever the properties of graphite it has, it is because of its different structural arrangement. So in graphite, it has a honeycomb structure. Yeah, you can see here, it is having a layered structure. So carbon atoms are arranged in different layers. So here this is one layer of carbon atoms, and below that this is one more layer of carbon atoms, and this is below that there is one more layer of carbon atoms, and each layer is known as graphene. Each layer is known as graphene. Okay. So here, if you see in this layer, in one particular layer, if I take one particular carbon atom, say suppose if I take this carbon atom is covalently bonded to 3 carbon atoms. So this is one carbon atom, and this is one more carbon atom, and this is one more carbon atom. So this particular carbon is only bonded to 3 carbon atoms only in the same layer. So we know that carbon has 4 valence electrons, and it is capable of forming 4 bonds. So what does the 4th valence electron will do? The 4th valence electron of each carbon atom is present between the layers and is free to move about. So the each carbon has 4 valence electrons, but each carbon is only forming 3 bonds. So one electron is free to move, and that electrons, they move freely in between the layers. So here the carbon, the valence, the fourth electron is free to move between the layers, okay. And you can see, so what is the type of attraction that holds these layers together? That is the weak van der Waals force of attraction. Okay, so these layers are held together by weak van der Waals forces of attraction. So since these van der Waals forces are weak, the layers can easily slide one over the other. So that's why graphite is soft. It is soft, and due to the presence of these free electrons, mobile electrons, graphite is a good conductor of electricity. And it is also, because of the slippery nature, it is also used as a lubricant. Okay, so this is about the structure as well as the properties of graphite. So let's summarize whatever we learned about the classification of crystalline solids. So first I covered about the molecular solids. In molecular solids, I discussed about non-polar, polar and hydrogen bonded. And in molecular solids, the constituent particles are molecules. And I also shown here the attractive forces. So in non-polar we have dispersion forces. In polar we have dipole-dipole attractions. And in hydrogen bonded we have hydrogen bonding present. And there are examples are also given. These are examples. And the physical nature is also given. I told that non-polar solids are soft, and because of the strong hydrogen bonding, these are hard. And electrical conductivity is also given. All are insulators, and even the melting point is also given. Because of the weak van der Waals force of weak dispersion forces, its melting point is very low, but polar is relatively high, but it is still low. Hydrogen bonded, it is low. Okay. So this is about molecular solids. Then I discussed about ionic solids, which is having ions as its constituent particles, and the attractive forces are Coulombic or electrostatic forces. Examples are given. All these are ionic solids. Due to the presence of strong attractions, these are hard and brittle, and they are insulators in solid state, but they are conductors in molten as well as aqueous solution state, and they are also having high melting point. And third one is, in this part, in this video, I discussed metallic solids and covalent solids, and I discussed about the constituent particles. In covalent solids, there are atoms, but here it is a positive ions in a sea of delocalized electrons, and here the attractive forces are also given. It is a metallic bonding, and here it is a covalent bonding, and these are metals: iron, copper, silver, and here it is diamond, graphite, quartz are examples. Okay. So the physical nature and the melting point, electrical conductivity is also given here. So this is all about the classification of crystalline solids. Okay. So depending upon our understanding, so let's test our understanding in this particular part. Okay. So for that, we'll solve some MCQs, multiple choice questions we'll solve, and let's see how much we understand this particular topic. So which of the following is covalent solid? Options given are NaCl, graphite, iron, iodine. So 4 options are given. So we want to find out which is a covalent solid. So NaCl is not a covalent solid, which is an ionic solid, and graphite is a covalent solid, iron is a metallic solid, and this is a iodine is a non-polar molecular solid. So which is a covalent solid? Option will be B. So B is going to be the correct option. Okay. So let's move to the second question, second MCQ. Which of the following is a good electrical conductor? Good electrical conductor. Solid NaCl, graphite, diamond, all of the above. We know that diamond is not a electrical conductor. So diamond you can erase, all of the above you can erase. We know that ionic solids in solid state does not conduct electricity. So this is also you can eliminate, and graphite is the only good electrical conductor. Okay. So this is also a simple question. So moving to the next one, the last question. The dipole-dipole interactions are present in. Dipole-dipole interactions are present in. So dipole-dipole means permanent dipole. So SO2, which is having a dipole moment. So this may be the answer. So let's also check the other options. Hydrogen, which is non-polar molecule, and it is not a dipole. So H2 is not dipole-dipole interactions are present. I2 is also not. CCl4 is also a non-polar molecule. So non-polar molecules are not going to have dipole-dipole interactions. Only the molecules which are polar in nature are going to have dipole-dipole interactions. So SO2 is going to be our answer. So A is going to be the correct option. Okay. So this is all about the classification of crystalline solids. So students, in this part we discussed about metallic solids and covalent solids as well, and their properties also. So I think you got the answer to my question which I have asked you at the starting of this particular part, that why the diamond is the hardest substance known. It is because of the covalent nature of the bonds and the network kind of lattice. Okay.